Hello, I welcome you all in this course on mechanical measurement systems. Today we will discuss second order system, ramp response, and we will focus on ramp response only. Second order system. And we will focus on a ramp response. It means when there is a ramp input in a second order system, how system is going to behave. Now, before we start the ramp response, I would like to mention here that in case of step response of second order system, recently we have discussed step response of second order system where input is instantaneous, and remains constant. Now, in this ramp response, if I say the system is underdamped, when the system is underdamped, there are going to be the vibrations. And after a certain time period, this is omega t, and this is qo, qik. Qo by k divided by qi. Qo by k divided by qi. Right? Then we will have vibrations. Now, suppose this is for underdamped system, it means zeta is less than 1. Now, suppose zeta is equal to 0.001. In that case, it is obvious that in that case, we are going to have vibrations of larger amplitude, and they will die after a long time, very long time, right? And this type of input or this type of response for a measuring system, I mean, it is not appreciated. A measuring system response should stabilize as early as possible. So that is why last time I told you that the damping ratio has to be in a range of 0.6 to 0.7 or can go up to 0.8. So there we strike a very good compromise between the oscillation and the sluggishness of the response of the system. Right? Now we have like piezoelectric transducers. So piezoelectric transducers have a quality. When a force is applied against the opposite faces, EMF is generated, or by applying EMF against the opposite faces, the deformation will take place in the crystal. Now, piezoelectric crystal, it has zeta or the damping ratio of the order of 0.001, right? Then step input was given to this crystal, and it was found that it is not responding like this. The response is very, very much acceptable, right? Now, the reason being then the analysis was done, and the reason was found that first of all we should understand that no model can truly represent the actual system. There has to be, or there will be, a deviation between a model and the working of actual system. So when we say there is a step input in the system, it is not exactly step input. The input is something like this. Right, this is let us say time, and this is qi. So the system will take some infinitesimal time. It may be in milliseconds. This may be in milliseconds, but there has to be some infinitesimal time for increasing the input from 0 to this value, QIS. Now, this type of input shall it alter the response of the system? Now the question is, if this type of input is given, shall it alter the response of the instrument? Now we have to see that mathematically. Now this type of input is known as terminated ramp response. Terminated ramp input to the system, and we have to see the terminated ramp response of the instrument. Now for terminated ramp input, the input becomes 0 here, change in the input becomes 0, or slope of the ramp now, or the input becomes constant after this. So there are two parts of this input, as we have done earlier in the transient response, that is for time interval t. So here it is divided in two zones. One zone, that is t is less than or equal to t, and another zone when t is greater than or equal to t, and it can go to up to infinity. For this, now again we will start with the basics of second order system. So first of all, we will write equation for the transient response of second order system, that is d square by omega n square plus 2 zeta omega, d by omega n plus 1 multiplied by qo is equal to k qi. And we can have higher order terms also on this side, input side, but because this k qi is good enough to represent many of the engineering systems, so we confine ourselves up to k qi only. Qi is equal to, there are two cases, input cases. One is t by t, right, when 0 less than t less than capital T. And then another one is 1, when input is 1. Let us take input, and this is the steady state value, and it will continue to be 1, right. Now output is dqi by dt is equal to 0 at t is equal to 0, right. Now for these boundary conditions, we have to find solution for this, and solution for this for all the cases. All the cases means when the system is overdamped, when system is critically damped, and when the system is when the system is underdamped, right. And for both the parts, in case of terminated ramp input, so there is a variation of input and then the input is constant. So both the parts we have to find a generalized equation, and for overdamped system, so we will start with the cases for underdamped system, because most of the systems, which are having very low, because this terminated ramp response is only for the system where the damping ratio is 0.01. Right. So when the damping ratio is very close to 0, or damping ratio, let us say 0.001. So ideally we should have calculated for overdamped, critically damped, or underdamped. But this terminated ramp response is useful only, this analysis is useful only in the case when damping ratio is very, very low, right. So now here, after just putting these boundary conditions here, as shown here, we get the output Q by K is equal to T by T then 2 zeta by omega n plus 1 by omega nt under root 1 minus zeta square e raised to power zeta omega nt, then sine under root 1 minus zeta square omega nt plus phi. Again the phi is the phase angle, and this equation is valid for only when time is greater or is less than or equal to time for terminated ramp response, because the time for terminated ramp input is up to this only, right. So we have got one equation for this. Now another equation for, we have, this equation is valid when time is greater than t. Then Qo by K, we have taken the previous expression as it is, and then it is minus another expression, and both the expressions have certain common terms and certain different terms as well. And the phase angle here in this case is 2 tan inverse under root zeta square by zeta, right. So this is the case when time is greater than capital T. I mean when the terminated the ramp input has stopped, and it can go up to infinity. So this is a pretty long equation, and I have not gone into the details how the equation has been driven, because as a mechanical engineer we are mostly concerned with the application side of the things, right. So instead of going into the details or intricacies, mathematical intricacies of driving this equation, I would like to discuss the implications of this equation. Now implications of this equation is that there is a steady error of the size. In this equation we will find that there is a steady state error. Now steady state error, SSE, steady state error is of the size of 2 zeta divided by omega nt. So in terminated ramp response there is a steady state error, and steady state error can be expressed by this. Now here, if the t is very small, if we make omega n very high, even for that, if t is small and the product has to be high, much higher than this zeta, then steady state error will be reduced. So if we take the piezoelectric crystal, for piezoelectric crystal the frequency is, let us say, 10 to 5 hertz, right. T is some milliseconds, right. We will take one example for this, and then if the zeta is 0.001, in that case the order of the error will be very less. That we will discuss later on. Now first of all, let us discuss about the response of the system. Now how the system is going to respond. Now for this, using these equations, some curves have been drawn. So like this, for example. Now first curve is about time versus Qo by K, okay, and this curve starts from, let us say, point 0 to 0.006. I am taking example of piezoelectric crystal where zeta is 0.001. Right, and for example, the ramp response is terminated approximately 6.3 milliseconds, or exactly 6.28 milliseconds. So capital T is 6.28 milliseconds for very short duration of time, because this cannot be 0. In ramp input it is 0. But for actual input, even though we want to have, for step input it has to be 0. But in actual practice we cannot have 0 to certain value in 0 time interval. There has to be some time interval, and for here we have assumed the value 6.28 milliseconds, right? And right now we will see the output of this crystal, this output characteristics. So for the output characteristics, we divide in two parts. One curve is for 0 to 10 into 10 to power minus 3. So 2, 4, 6, 8 and 10 milliseconds. Now input is Q by K, right? So it is starting from 0.02, 0.04 and up to it goes up to 0.020, 10 times, right? And then we will say this is the input, it is 0.628, so it will come somewhere here and the input is like this. This is the input, this is the ramp input. Now for this ramp input, the output of or the response of the system is like this. If it was vertical, then remember we could have observed the vibrations, but it is a ramp. In the ramp, the deviation is not much. Now ramp is terminated somewhere there, right? So now we will draw another curve. In this curve, we will take the time beyond 6.24, right? And we will come somewhere here. Let us say 6.3 milliseconds, and then let us say 6.4 milliseconds or 10 to power minus 3 seconds, right? So this will involve both response of ramp and as well as steady input. So now here this is 1.0 and here is 1.002, right? And there is a unit input. As you said, there is a input is like this. Input is, we have taken unit input, so input is like this. Now the response of the system is going to be like this here. So what I mean to say, for this also there is not much deviation, and when the input ramp is completed, in that case also the deviation is not much. So there is an excellent response. We should say there is an excellent response of the system for terminated ramp input, right? Though if we give, ideally if we give the step input, there is going to be a lot of vibrations in the system, in the response of the instrument. So error in this type of measurement is, I said you earlier, that it is 2 zeta by omega n t. Let us take one example. There is a pressure pickup which has damping ratio as 0.01. So damping ratio is 0.01 and natural frequency is 1 lakh. Omega n is 1 lakh cycles per second. Okay. No, sorry, this is omega is not cycle, it is radians per second. It is radians per second. Okay. And subjected to the ramp input with T is equal to 0.628. T is equal to 0.628. Right. So, so transient error in percentage is going to be equal to 2 times zeta divided by omega n, or for 1% error it is going to be 1 by zeta omega divided by omega n. Okay. So for 1% error it is going to be zeta divided by omega n t, right? And you can see from here, if you are putting the value, because this low value of t which could have incurred very high error is compensated by very high value of natural frequency. Now we will take an example of pressure pickup. In a pressure pickup where the piezoelectric transducer is used, the damping ratio is 0.01 and natural frequency is 100,000 radians per second. So the damping ratio 0.01 and natural frequency is 100,000 radians per second, right? And if the terminated ramp input is let us say 0.628 milliseconds. So if you remember, in denominator there is a term in the error omega n t. So when we write this omega n t, though it is for a very short duration of time, if frequencies or the Wn natural frequency is substantially high, as in the case of piezoelectric crystals, then the product of these two is going to be 100 multiplied by 0.628 or 628. This is multiplied by zeta n, zeta, that is damping coefficient. The error is 2 zeta. So final error is going to be very insignificant in the response of the pickup, and the response of the pickup can always be shown as, for this type of input, the response is going to be like this. It will closely follow this line, right? Now after this we will take the ramp response of measuring systems. In the ramp response of measuring systems, is the second order system, ramp response second order system, ramp response. If you remember, in the first order system we have taken a ramp response as something like this. Suppose this is ramp input, then the output, ramp output, we have taken something like this. Right? And there is a steady state error in the measurement, or there is a time lag and steady state error in the measurement in the first order system, and it was transient error was minus q dot is lambda e to power minus lambda t. That was the transient error, and the steady state error was q dot is lambda. So this is the steady state error in the measurement. Now here also we have for ramp response, for the same initial conditions as in the case of step response, there is a final equation. This is for the damped case when zeta is equal to, here in this case, now we are going for the full-fledged ramp response. We will derive equations for all three cases: when damping coefficient is greater than 1, when system is critically damped, and when the damping coefficient is less than 1. So when the system is overdamped, in that case the output or the response of the system is expressed by this equation. This appears to be a very complicated equation, And normally, because normally our systems have the damping ratio in a range of 0.6 to 0.7. So normally our systems, second order systems, are followed by the equation, governing equation by underdamped system, and that is QO by K. This is rate of input minus this expression. The angle, phase angle, can be calculated by using this equation, which is a function of damping ratio. So phi in underdamped system, the phase angle phi can be calculated by using this equation. So it is a function of damping ratio only. And if we want to show the error in the measurement, when there is a ramp input, what is the error in the measurement? So like first order system, we can have a graph for second order system also, because as a user, we are more concerned with the error in the measurement, right? So error in the measurement for second order system ramp input is going to be zeta is equal to 1.5. It is going to be like this. For zeta is equal to 1.5. This is overdamped system. For a critical damped system, so this is, let us say this is 1. For critically damped system, this is 1. For critically damped system, it will go like this. This is zeta is equal to 1. For underdamped system, there is going to be change, and the change is, let us say zeta is equal to 0.4. The change is going to be like this. It's some degree of vibrations, and that will also incur error in the measurement, and that is equal to 0.4. Right? Now, when the system is stabilized, the system is going to have a steady state error, and if we draw a curve between time and the output then suppose this is ramp input to the system. This is ramp input to the system, right? Now, error in the output. Initially, there is going to be some error, but after a certain time interval, there is going to be a steady state, and there is going to be a steady state error, and this steady state error as I mentioned earlier, it is 2 zeta QIS rate divided by omega n. So this is the steady state error in the ramp response of, in first order system, it was QIS rate multiplied by lambda. Now here this damping coefficient has come into the picture, and natural frequency has also come into the picture, and this time constant has gone. And there is a time lag also. There is one steady state error. It means for this input, output is this much. So this is steady state error. And this one is time lag. So in a ramp response, there are two things. One is steady state error, that is at a particular instant, what is actual input and what is input indicated by the instrument. And there is another is time lag. Time lag means this input is shown at this time, actual system is responding for the same, showing the same input at this time. So this is the time lag, and time lag is represented by 2 zeta by omega n. This is the time lag in the measurement, and this is steady state error in ramp response of measuring instrument. So that is all for today, and in the next lecture we will start with the impulse and frequency response of second order system.